into practice that the people building and using these systems can rely on. And that's an important kind of fourth domain to consider when we talk about space security research. So over the course of this talk, I'm just going to touch on some topics that personally excite me in each of these four areas. And hopefully that'll get you all thinking a little bit. I know that lots of the papers at SpaceSec already touch on some of these topics and are kind of pushing the needle forward on some really important research questions, but hopefully I can pique your interest and kind of build a general theme around what's happening in space security research. So in the ground domain, we've seen a lot of really exciting developments lately. One is the evolution of ground stations as a service, this idea that you don't need to own your ground station to run a satellite mission. Instead, you can rent ground stations on a minutely basis from providers like AWS or Azure and just use the ground station for the period of time you need, and then someone else can use the ground station after you. We've seen an increased push towards this idea for direct-to-mobile receivers so that your cell phone itself or your autonomous vehicle might connect directly to a satellite rather than via some intermediary hub like a Wi-Fi antenna. We see an increased use in commercial observation of space. So there are increasingly operators running radar systems and telescopes on the ground to tell people what's happening in orbit, whereas traditionally that's been a government enterprise for the most part. And we've also seen a push towards more software-defined ground stations for receiving and interpreting this data, and a push towards more autonomous flight control systems where perhaps there is a single centralized compute authority that's determining how a satellite network might maneuver around itself rather than individuals planning these maneuvers and then keying them in telemetry commands. So one area that's really interesting to me is this idea of a trusted ground station. When we think about ground stations as a service and you borrow someone else's ground station for a couple of minutes, how can you actually know what messages that ground station received and if those messages are accurate and haven't been messed with? Is there any way that you can bring integrity to a ground system's data that's being run by a third party? And kind of from the attacker perspective, if you control a ground station and you're relaying information and you're reporting that that information is perhaps raw radio data, like raw IQ data, or maybe some like minimally processed data at a protocol layer above that, what kind of lies can you inject into the signal that might deceive someone who is using your service? What kind of deceptions could you make as the owner of a malicious ground station? And in particular, there are some data formats that are very obvious and easy to encrypt and sign, but there are other data formats that are perhaps a little bit more complicated. For example, when you don't own the satellite that is broadcasting that data and it's a streaming data format, like it's the imagery that comes off of a NASA weather satellite or an Earth observation satellite. These satellites have set formats. They aren't going to be modified. Is there any way to still enforce trust in a third-party ground station when you don't have control over that format or that data, and when you have no influence over the protocols or satellites that are sending it? And I think that for people who have interest in cryptography or in radio signaling, there's a lot of really deep work that can be done around making third-party ground stations more trustworthy. Another area that kind of follows this theme of an untrusted ground station is this idea of terminals that are pushing closer and closer to the end user. We've had satellite phones for a long time, but historically, the devices that connect to a satellite broadband or a satellite communications network have all generally been under the control of the service provider. They manage the firmwares, they update the devices, they control the hardware. And as we move towards a more direct-to-mobile satellite communications ecosystem, or an ecosystem like we saw with the Starlink devices that can be modified to have hostile devices, we might think about what happens when untrusted devices join these satellite networks and what kind of monitoring and controls can be put in place. And I think that this is particularly interesting when we think about what an attacker might do with a device inside a network. Denial of service protections of satellite networks often assume the attack comes from outside the network. But what happens if a terminal inside the network starts to behave maliciously? Or what happens if they try to saturate critical routers or critical transponders on the satellites that are communicating, and what harms could they do? And then how would we defend against this? A lot of the ways that we can authorize devices in terrestrial wireless networks where we have third-party devices are very chatty. So when you bring your cell phone and connect it to a 5G or an LTE tower, there is a lot of back and forth conversation. And back and forth conversation is really expensive when it has to go all the way up to geostationary Earth orbit or all the way through a low Earth orbit constellation before it could be resolved. So we might think about ways that we can come up with more performant ways to detect malicious behavior or to query devices and ensure that they're trusted. Another topic area that's kind of peripherally related to this as well, and this idea of an untrusted ground station, is from the idea of protecting the person who's running that ground station. One of the dreams that has been kind of pushed around the next generation of satellite internet, this globally available internet connectivity, is this idea that it might be used to get around censorship, that people in regimes that are limiting their communications or access to information might use satellite terminals to get past a firewall or get past a global internet block that's being employed at the national level and communicate and get information that they need. One of the problems is that satellite terminals, especially the ones that transmit information, can be very noisy. Starlink terminals emanate a ton of electromagnetic energy. Their radio waves are very loud. Their side loads are basically unfiltered. And that's true for almost all active satellite communications. And so we might think about what we would do to design a terminal that is stealthy, that doesn't emanate as much radio waves when it's being used, or that can be used in a secure way. And I think even more importantly, how we might enable that to be done to existing satellite terminals or third-party terminals aftermarket in a way that someone who is in a regime that's influenced by censorship might be able to employ at home using hardware they can buy at a local shop, but with reasonable confidence that those modifications will, one, not impair the ability of their device to communicate, but two, impair the ability of authorities to detect that they're using these devices. And I think this is a really interesting privacy question that's emerging in space, and something that people with like hands-on hardware chops could really contribute to. In terms of the radio communication systems, it's not just about kind of the ground terminals and what they do. We're seeing all kinds of changes in how satellite communications and radio links between space systems operate. One of the biggest developments is this idea of optical links for satellite communications. They have all sorts of advantages. You don't have to worry about fighting the regulatory battles for spectrum quite as much when you're using point-to-point laser communications, which for space, where the coverage areas can be quite immense, can be really useful. And then there's also some performance advantages and speed advantages in direct, like laser or point-to-point links. We're seeing a push towards secure protocols. Historically, satellite communications have been unencrypted under the assumption that nobody will be able to intercept those communications. That's starting to change, both in like the satellite broadband space, but also in the satellite telemetry and control space. And as these protocols are designed, I think there'll be a need for security researchers to vet that what industry is building actually meets the security promises that it's claiming to make. There's also the world of inter-satellite communications. The days of a bent pipe where there's a single satellite in orbit and you send your signal up and then it comes back down are starting to grow to an end. And we're seeing increasingly messages that route between many different satellites. We're also thinking about deep space missions to the moon and to Mars that will require deeper communications that still have security requirements. And deep space is its own environment. The power levels that are required to transmit reliable signals over those distances are quite high, and the tolerance to noise can be quite low. There's quite a bigger consequence to disruption. And then you also have huge amounts of latency when you start talking about like interplanetary networking. And these are all questions that will need to be solved as we start to build towards future exploration on Mars and beyond. And then there's also this question of internetworking, which is networking between different satellite operators. So right now we have this model where, Iridium runs their own network, Viasat runs their own network, Starlink runs their own network. But we might see a future where a message hops between many different satellite internet service providers. And we might think about what kind of trust and routing protocols will be needed in that sort of domain, much like we've built out for the internet as we've moved towards a community of different providers working together to run what we call the internet. There's also a lot of energy around this idea of quantum key distribution using satellites. To be honest, it's an area well outside of my area of expertise, but it may be within yours. And I think there is quite a lot of excitement around the role of quantum communications and quantum key distribution in space communications going forward. For me, though, one of the areas that I think is worth delving a little bit deeper into is this question of optical links, because it opens up a lot of questions that I think folks with a lab setup could get resolved very quickly and very impactfully. One big question is, we know how to eavesdrop on satellite radio signals. We know what an attacker can do. When we think about more directional point-to-point optical links, are they immune to eavesdropping? Are there particular positions or techniques an attacker might use to pick up these signals? And are those techniques different if we're talking about from one satellite to another satellite in orbit versus a satellite to an optical transmitter or receiver on the ground? And I think there's all kinds of exciting things you might do with like balloons and drones and mirrors and all kinds of fun stuff that could lead to some really interesting answers to these questions. Likewise, there's the question of if optical links are integrous. They operate at the speed of light. They're very directional. It might be harder for a man-in-the-middle attacker to be able to intercede in these signals without getting detected, or to manipulate or inject information in these signals when you compare it to radio or kind of more like networky, kind of higher level protocols. And I'd be really curious to see what an injection attack looks like in an optical communications link, and how you could target those injection attacks against space-based assets. And then finally, there's the jamming and availability question. We know what radio jamming looks like, and radio jammers have a huge advantage because radio waves are so broad and they're not quite as directional. But I think there's definitely a question as to if an attacker with an optical transmitter and enough information about the target system could reliably dazzle or otherwise disrupt communications from an adversary, and what those threats actually look like and how they might be implemented in practice, especially when tracking an object that's moving around in orbit. Another area that might involve optical communications, but could also involve radio communications, is the way that satellites talk to each other in orbit. We've seen constellations going into orbit recently that involve intersatellite links as a key component of routing messages. And there are questions around what an attacker could do if they had control over which messages get into the network. Could they undermine the performance or behavior of that network in some way? There are also questions about if there are key satellites or key nodes in that network, which might be a point of failure that could be compromised either via malware or even kinetic anti-satellite weapons. And if so, what effect that would have on the network, and if there are resilient routing protocols that could be more robust to those kinds of attacks. And there are also questions about what if a node is run by a third party, like in that internetworking scenario I gave, or if a node is compromised or untrusted in some way and decides to misbehave and route messages incorrectly. Is there a way to detect that behavior and to correct for it in the network? And what would that look like in a network where every node is shifting in physical relationship to each other as it orbits the Earth? Finally, on the deep space communications topic, I think that there are all kinds of challenges I outlined around latency and bandwidth and reliability that create really interesting security questions, like how do we mutually authenticate a Mars rover and a node on Earth sending commands to it when every command takes, I want to say, 8 minutes to get from here to there, and we might need to get commands across with faster round-trip travel times. And so thinking about what's the minimal amount of chatter that can still provide the sort of security guarantees we would expect from modern cryptographic protocols, and how that might be implemented in extremely high delay environments could be really important. We might also think about how we can deal with jamming and disruption attacks in these environments, what failsafe looks like for communications in deep space, and how we can deal with situations where we might know a message has been compromised or corrupted, but it's still too expensive or too long to retransmit. And if there's ways that we can forensically reconstruct or recover enough data to make a reasonable judgment, if they're like error correction techniques we might employ that work even in a case where retransmission is just not an option because it takes too long. In terms of the platforms themselves in orbit, there are also some really exciting developments happening here. that I think folks at the conference will have thoughts on as well. One is this idea of satellites as becoming more of an off-the-shelf object, where there is like a satellite operating system that multiple satellites will run, and they're not quite as bespoke. And kind of following that trend, this idea of satellites as being a platform that other people could rent or borrow. So you might launch a satellite with a sensor suite on it, and then different researchers or universities or governments might rent time on your satellite to use that equipment. You might think about how we design secure satellites with multiple tenants on them. There's also increasingly the use of satellite hardware to do processing in orbit. There might be pre-processing of images, to example, filter out certain data that's known to be irrelevant, or might be even more involved processing, like automatically tagging or alerting based off of certain information coming in on sensors. And we might think about as satellites do more complex information than just relay raw sensor data from a sensor via radio to Earth. What kind of vulnerabilities might be exploited in that processing pipeline? There are also increasingly advanced and capable sensors that are basically compute systems in their own right. And I think there's some just applied vulnerability research to be done on these devices, these hardware modules that are being built for satellites, and what security properties and trust models are involved in attaching one of those to your satellite. And we're also seeing satellites get smaller and more integrated, whether that's through swarms of satellites that coordinate together to complete a mission, or very small and inexpensive satellites that may be launched for tens or hundreds of thousands of dollars instead of millions of dollars. And then, as I mentioned before, I think one really exciting area is kind of these more unusual vehicles that go beyond satellites. So whether that's launch vehicles, which are becoming increasingly capable, these are no longer just candlesticks that you light at one end and they go to space. They can often do a lot of maneuvering and decision-making and even returning back to Earth on their own right. And so thinking about how we secure these complex launch platforms and how we secure the sort of platforms we're going to be building in orbit, whether those are next generation space stations or moon bases or rovers. As we start thinking about building hardware to operate in space, I think these requirements and design decisions we make as a security community will end up having an outsized impact for decades to come. So one area that I think people have already started work on, and I think will be fruitful for a lot of security research, is this idea of the hardware bus on a satellite and how we protect it when we have increasingly complex and integrated communication systems. So we might think about how an attacker could send messages across a radio on a satellite in such a way that it has an effect on the bus that's being used to communicate that message back to the flight controller. And if an attacker could overwhelm a bus with messages that are crafted in a particular way, or if they could cause effects such as causing messages to be dropped from other hardware on the satellite due to what they're pushing into the radio feed remotely. We may also think about onboard attackers. Maybe a camera module on your satellite has a backdoor that's been put in by the hardware developer or somewhere in the supply chain, and how we could take this device and prevent it from issuing commands to other devices on the satellite. So right now, if you've got a camera on your satellite and it's plugged into the same bus that your flight control system is, there's nothing stopping that camera from issuing messages as if it was the flight controller and causing your satellite to engage in a maneuver. And we might think about ways that we can design satellites to better mitigate that untrusted environment once you get onto the platform without reducing the reliability that aerospace people require for their missions, where these messages absolutely need to get through when they are authentic. And that's kind of the final question here is, if we do come up with security controls, a sort of rider for satellite buses, can we be 100% sure that every message that needs to get through will? And can we drive false positives in anomaly detection or intrusion prevention to as close to zero as possible? Because the tolerance for a false alert or a false failure to send a message on a satellite in orbit is way, way lower than just an extra pop-up on a Windows system log somewhere. And so thinking about building intrusion control and intrusion prevention systems in an environment where false positives are basically unacceptable, I think is a unique variant on a challenge that the security community has worked very hard on for a long time. Likewise, when we think about launch vehicle security, this is another environment where mistakes are not an option, right? These are incredibly dangerous devices. If there is a launch anomaly, it can hurt people on the ground, it can kill people, it can be seen as an escalation in all kinds of dangerous ways. These are basically missiles, and if they stray from their path, they can provoke all kinds of panicked responses. And so thinking about, as we have tons and tons of people building startups or kind of larger space companies that create next generation launch systems, what does it mean to have a certified secure launch system from a cyber perspective? And what are the requirements for verifying and validating that those systems perform in that way? And as you increasingly have launch vehicles that you might buy from someone else or rent from a third party or share with multi-stakeholders, how can you be sure that everyone involved in a mission that may involve dozens or hundreds of companies is compliant and secure and non-malicious, that they're all trustworthy? And I think that this involves a shift that the space industry has generally struggled with, from this idea of safety, and where if there's like a couple that's likely to fail, you have two of them so that if one fails, the other works. And security, where if someone lies, they're just as likely to lie twice. And the difference between those two threat models is something that the aerospace industry is still grappling with, this idea that it's not just about probabilities and reducing risk through redundancy, but there's also an intelligent, malicious adversary that can cause mission failures. And so characterizing this in launch vehicles and other very safety-sensitive topics in space could be an important contribution that folks in this domain can make. The last thing that interests me for this talk about space missions is this idea of people being in space. We've had people at the International Space Station for a long time, but there's increased energy in getting both tourists and researchers and astronauts to do more in orbit. And those astronauts are expecting more than ever before. Once upon a time, it was really neat to be able to have a phone call with the president from the space station. But now we're expecting live video chatting and connectivity basically continuously from in-orbit platforms, whether those are just devices to keep astronauts entertained or devices to allow them to do their work. And we need to think about what it means to take a traditional IT system that an astronaut might use and ensure that it's secure in a non-traditional surrounding where it may be plugged into the same network that's connected to a rocket or connected to a life support system. And we need to think about what the requirements are on the humans who are in space in terms of cybersecurity, and how we can create protections around the people in space to ensure that things that would be like mildly bad, like downloading a piece of malware onto your personal computer on the ground, don't become tragic because you happen to download a ransomware while you're on the International Space Station. And so thinking about security, just general IT security, but in this new environment, is also a place where there could be really big impacts. The final topic area I'm going to touch on very briefly is this idea that it's not just about the technology, but also about kind of the regulatory and policy environment, whether that's the spectrum that we allocate to space missions and how we ensure that countries respect different countries' allocations to the spectrum, whether it's about how we protect the space environment, orbital debris, alerting people of our rockets and our maneuvers so that we don't have orbital collisions, and whether it's talking about who owns regulations domestically, who's responsible for being sure that everything that goes into orbit is sufficiently secure to some standard, and also what's appropriate and suitable both in terms of when you're building a rocket or building a space mission, but also in terms of the international norms that we have around space missions. What is a red line in terms of digital counter space attacks in international law, or in terms of how countries are supposed to treat each other's space assets? And are those different in how countries treat other cyber assets? So in terms of international coordination, I think there are all kinds of really important questions that countries will need to resolve around space security. And they will turn to experts like you all in the audience to help them answer these questions and understand the consequences of their answers, whether that is in terms of allocating spectrum to different entities, or in terms of determining when a jamming attack or an interception and eavesdropping attack is suitable and by whom, For example, if a satellite is floating over my territory, but it's not my satellite, am I allowed to jam it? What if I'm just jamming the downlink that's coming into my country as a means of censorship? Is that an attack on someone else's space asset? These policy questions will require people who understand them technically to be able to answer and inform the policymakers who are making those decisions. We might also think about orbits. There's increasingly fights over geostationary Earth orbits as they get more crowded, but also around other high-value orbits, and thinking about how countries can coordinate and share those resources. And also which countries are responsible for environmental harms. If a cyber attack through negligence causes a satellite to break up and create space debris, does a country have an obligation to clean up that debris? If a cyber attack that's malicious creates space debris, does a country have a diplomatic obligation for the environmental harm that they've caused? We might also think about regulations at home. So in addition to what countries should do with respect to each other in space, there are huge questions around which regulatory bodies in each country are responsible for verifying that space missions are secure and how they should do that, whether or not all space missions should be treated in the same way, or if there's a difference between your university CubeSat project and the next International Space Station, and also how we enforce that, how we incentivize the space industry to build and secure their systems. So hopefully that's been a whirlwind of ideas and thoughts and topics that I've been thinking about in space. And I'm sure many of you have been thinking about some of the same topics. But I think the key takeaway is that the work that you all are doing at this workshop and that you've been working on really matters. Space is going through a time of transformation, whether that's in terms of the ground systems that we use, or the signals we communicate with, or the platforms in orbit, or the policies that we put around them. And the contributions that you all make in your research and in your work together will have a lasting and dramatic impact on our ability as a species to make use of outer space. We're designing space missions today that will determine what space looks like for the rest of our lives. And the contributions that you all make will determine a lot of that in terms of safety and in terms of our ability to trust the domain. So that's the question I leave to you all is, what will you explore next in space? What's the next space security topic that excites you? And thank you so much for listening to this keynote. Again, I'm so sorry that I wasn't able to be there in person. And I would really encourage you all, like everyone at the conference, to reach out to me whenever you feel like it and have a chat. I love meeting people who are working in this domain, and I love chatting with you all and would love to learn more. And yeah, thank you so much for listening, and I'm happy to answer any questions if that's something we can do technically from remote. Otherwise, happy to hand it over to whoever's next.
My name is Knut. I work for the European Space Agency for 16 years as a security engineer. And I would like to use this as an opportunity before I start commenting on the keynote to have a little poll in the room just to see what the awareness of certain technical solutions is. I still have to get it closer. Okay, yeah. Okay, so I'd like to know in the room for whom does CCSDS ring a bell? Okay, that's like 3, 4, 5. Okay, that's like the IETF of space. It's the Consultative Committee of Space Data Systems, and their standards are being developed. And there's actually one standard for securing the RF links. That's called SDLS. Who has heard of that before? SDLS. Yeah, it's the same, more or less the same for guys. 5, yeah. So that is actually how today some of the missions are implementing that. I just wanted to see what is the awareness of that. The documents are public, and for sure it would be interesting to have a review from a research perspective. The protocols are not extremely complex, but extensions are being worked on, for example, key agreement protocols and things like this. So yeah, for me, a quick comment, ground station as a service is not that new. That's been something that's been around for quite some time in the shape of commercial ground stations. So if you need extra capacity, you can go to companies like Swedish Space Corporation or KSAT, and they for like $1,000 per hour, you can use a professional station. And typically the security, there was some interesting comments from James how you could increase the security mechanisms. where you want, let's say, positively identify your satellite, for example, through radio fingerprinting. That could be an interesting idea. But today, those missions that have strong security needs, they encrypt at the link layer, and then there's a specific forwarding protocol that over TCP/IP you receive directly your frames. Quantum key distribution, don't get me started. That's a major thing where there's a lot of enthusiasm, but if you look at it just abstractly from a security, distributed system security researcher, is there any value in a security solution where you tie your encryption to the physical layer? My personal opinion is not, but I remain to be convinced, because we need end-to-end security, we need end-to-end encryption, and the success of the internet and many other things relies on the fact that we do things at abstract higher layers. We don't bind our security to a physical level. The same comment applies not just to QKD, but also to this information theoretic security or information theoretic coding, which has been along for quite some time. Yeah.
Anything specific to James still while he's on the line? Or?
Yeah, that was on the QKD. So, and optical, there's also a lot of enthusiasm on optical. It's actually very hard. And while RF for a CubeSat, you can actually buy a module very cheaply. People are still working. There was like 3-4 years ago a very enthusiastic wave. People wanted to build optical telescopes for small sats. This is super hard because the pointing accuracy that you need is unimaginable. It's like, imagine you're standing on the Eiffel Tower and you're actually pointing to the Empire State Building across the Atlantic Ocean, and you have to hit a dime. That's the pointing accuracy you need. And that translates also into stability requirements for your platform, for your satellite platform, because otherwise the control loop will not close, which has to point your terminal. So optical is super interesting, but is not applicable to every solution scenario.
Thanks. So I know we can do a keynote next year. Some questions?
Okay. My name is Yue Chen. I'm from Seoul, Bodo. So my question is about the availability of public research resources. So for example, if I want to, so currently the satellite onboard system just like black box to me. I don't really know what exactly is in it. So I asked my colleagues in aero engineering in Seoul, Bodo, so I can know, okay, there are some processors and some data bus. And it's very surprising to me is like we only have one data bus that generally used in all satellites, something like that. And also about the ground station, for example, the Starlink ground station. If we want to analyze and reverse engineer the firmware, we need to have a very expensive device to dump it. So it seems like really the only like public resources that we can have is the communication between the space and the satellite. So we need to overstrip on the communication. And I don't even know if even it's legal in the States. So if you know, please advise. So my question is about like, will there be some public research resources like some toy satellites or some toy ground stations to be used in the future? Yep. Yes.
I think there's a lot of initiatives around that. And I think it's definitely one of the hardest things about researching space security is the fact that like you just can't get at most of this stuff. And satellites are so bespoke and so expensive and so hard to work on that it can be very difficult to have any sort of research, much less like scientifically generalizable conclusions out of any experiments. I think there's definitely a push. I would encourage you to check out the Hackasat program, which DEF CON has been running for a few years now. I think this upcoming year, they're going to be launching like a digital twin, which is like a virtualized satellite environment, but it's just one instance of the satellite. It's not all satellites ever. I think the other way to go here is as a community, with conferences like this one, we can hopefully begin to build a reputation as not just like people who are looking to pull one over on the space industry and kind of make them look bad, but as like genuine security researchers who want to contribute our knowledge to help them be more secure and maybe win over some industry participants who will share access to their hardware or open up their specifications to researchers so that they can be more confident in the security. But I think it's a long battle and it's going to be a difficult one.
that would have been my question after your talk. What's your experience? Has this changed or improved over the past 5 years? Is there more openness towards, well, research really from academics?
It's definitely improving. I think that at least a few years ago, there was very, very little out there, and it's kind of the only option was to look at the radio signals. But we've seen, I think, in part, there's like generally this movement towards open source code, which has been going on for a long time, but is just starting to get into the space industry in a way that is really exciting. So we're seeing like NASA's release their core flight system. So you've got like source code for a real satellite operating system in C and emulators to run it. And so things like that, as they become more open, may be really useful for security researchers. And then we've also seen as the discipline has professionalized a little bit, and now we're at NDSS, and we've had Black Hat and then the DEF CON Aerospace Village, and we've had increasing papers at the big system security conferences. And as that happens, I found that people in the industry are not quite as afraid of security research as they once were, and are a little bit more open to talking about it.
And Fred, not so much a question as a comment following up on that theme. There's also the concept of flat satellites basically on a bench, just all the different components. As again, not at a price point that's effective for universities yet, but if you have, any department that's, launched these things, they might have flat sats around, or, my organization launches these, so we have some of them and something like that. That's another good way to get something that might be more effective for security researchers. Also realized I didn't mention my name. I'm Samuel Giroux, and I'm from MIT Lincoln Laboratory. So, yeah.
Well, yeah, I mean, that's awesome. Flat sats are a great idea. And I think, a lot of people who actually do space missions might be the ones to talk to getting started on security research.